question, you want to type it in there, go for it. I will try to keep one eye on it the whole time, right? So anyhow, today we're going to take a look at some practice problems from the textbook that have to do with chapter 9. And so we're going to start by naming some compounds. So this is just question 9.32. It's a nomenclature question. So the first thing we want to do is we recognize our functional group, right? The whole topic of chapter 9 is alkynes. Years ago, ACS had a conference and they were handing out bumper stickers that said it takes alkynes to make a world. Anyhow, you can see that the longest chain here contains 1, 2, 3, 4, 5, 6 carbons. There's no debate about that. But when it comes to where do we start, right? Because you see that the triple bond starts at 1, 2, 3. If I start numbering at that end, and it starts 1, 2, 3. So either way, it's some kind of 3-hexyne that we've got here. So we know this is some kind of 3-hexyne. And so as far as which end do we actually start numbering from, well, we would go to the next rule, and we want to give the first substituent the lowest possible number. Well, we have methyl groups at both carbon 2, whether it's the blue one or the red one, but you see that the red one has 2 methyl groups on it, so that would be the winner. So the proper way to number the compound is using the numbers I have in red and not the numbers that I have in blue. So let's erase some of that spinach. So we're going to say 1, 2, 3, 4, 4, 5, 6, like that. So we've got a 2, 2, 5. Because we have 3 methyl groups, we have to provide a locant for each one. 2, 2, 5, trimethyl, 3-hexyne. Remember, we always separate a number and a letter by a hyphen, and we separate numbers by commas. Okay, the next one. So now that we have the rule down, we can go a little faster on the next one because we see the longest carbon chain has a total of 6 carbons in it as well, but we want to give the triple bond the lowest possible number. So we're going to say 1, 2, 3, 4, 5, 6. And so we've only got 2 substituents, right? It's some kind of 2-hexyne in this case. It's a 2-hexyne. And so we're going to say we've got a 4,4-dichloro. So we say 4,4-dichloro, 2-hexyne. And I'm not going to pencil it down, but you could also write 4,4-dichlorohex-2-ine. And for the first one, you could have said 2,2,5-trimethyl-hex-3-ine. Either one is totally fine. The next one is, I'd say, even lower in complexity than the first ones. Here we have 1, 2, 3, 4, 5, 6. So this is 1-hexyne. Just some points about drawing the bond line structure of an alkyne. Remember that the geometry, the molecular geometry around an sp hybridized carbon is linear, and so the bond angle is 180 degrees. And so you never draw the triple bond like this and then put a line off of it like that. That's a big no-no, okay? Anyhow, it's something that people are prone to do when they're learning the subject, but once you get the hang of it, you try to avoid that. Okay, the next one, we have 1, 2, 3, 4 carbons in our longest chain, right? It might be tempted to say, well, it's only 3, but remember, you can go all the way up to the 4 here. So this is a 1-butyne. We have a 3-bromo and a 3-methyl. So B comes before M's, bromo comes before methyl. So we have 3-bromo, 3-methyl, 1-butyne. And again, you could call it 3-bromo, 3-methyl, but-1-ine. Either one is perfectly fine. So there you go, a little bit of nomenclature practice. If you know how to name an alkene, you can usually name an alkyne. Question 9.35 says draw the products of each of the following acid-base reactions and then predict the position of the equilibrium. So will the equilibrium lie to the side of the products, or will it lie to the side of the reactants? That's what we want to figure out. And the way that we're going to do that is by looking at the pKa. So here we have acetylene. This is the simplest possible alkyne in the universe, and this is butyllithium. If you don't remember, this is one of the bases that we said was strong enough to pull a proton off of a terminal alkyne. And it's not asking for a curved arrow in here or anything like that, but we could draw a quick one, and we could say, well, we're going to do proton transfer like this. So we're going to end up with the acetylide ion, and we're also going to end up with butane. And so if we go right back to the first principles, kind of an acid base from general chemistry, we have our acid, we have our base, our butyllithium is our base. This will be our conjugate base, and butane will be our conjugate conjugate acid. We'll talk about weak acids, right? Butane is an alkane, which has a pK of around 50, whereas the alkyne, acetylene, has a pK of around 25. So the equilibrium is going to lie to the side of the weaker acid. And so, yes, butyllithium is definitely an appropriate base for deprotonating acetylene. And so our equilibrium is going to lie very hard to the side of the products. Okay. Essentially, it's going to be an irreversible reaction. So I'll just leave it like that. We're going to have nothing in the reverse direction. All right. The next one, we're using sodium hydride. And so if you draw the Lewis structure of sodium hydride, you'd have to draw the sodium cation and the hydride anion like that. Again, not asking for a mechanism, but we can give one here. So we're going to end up with our alkanide, and I forgot to put in my equilibrium arrows with my question mark, but you guys get the idea. Okay, and so we have our acetylide, our alkanide, which is going to look like this. And then we have our conjugate acid, which in this case is going to be hydrogen gas. And hydrogen gas has a pKa that is equal to 38. And the alkyne, of course, has a pK which is equal to 25. And so, yes, sodium hydride is going to be an effective base at deprotonating a terminal alkyne. So we can erase that question mark. And we'll just say this is essentially an irreversible reaction. It's got a difference in pKa units that's greater than 10. And so it's just going to lie to the side of the product. So butyllithium, sodium hydride, and if you also remember, the other base that we said that was appropriate was sodium amide, right? We said that these were the three bases. So we had butyllithium, we had sodium hydride, and we had sodium amide. These are all effective at deprotonating a terminal alkyne. It's interesting that they put butyllithium and sodium hydride in this question, because the one that's most commonly used is actually the sodium amide. Okay, when we do the alkylation chemistry, and we're going to see some more of that this morning. Give me a thumbs up if you're with me on that, on the pKa's, and that the equilibrium lies to the side of the weaker acid, not the stronger acid. All right, cool. There we go. So a little nomenclature practice. Oops, some pKa's and equilibria practice. Well, I think question 9.37 is a great way to practice the individual reactions that we learned in the class. So it's just kind of, just one reaction at a time here. So this isn't, synthesis heavy, but it is a good way to practice your the reactions that we learned in the chapter. So we'll start with this one here. Some of the maybe the lower hanging fruit. So if we're taking the alkyne and we're converting it to an alkane, could anybody give me the conditions for this reaction? Could anybody tell me what the conditions would be for this one? This is where you want to kind of go into your mind and say, okay, well, what do I know to do this reduction here to convert the alkyne to an alkane? Yeah, thanks, Rubio. Absolutely. It's going to be hydrogen gas, isn't it? Right, so we need hydrogen, and then you can pick palladium catalyst, platinum, nickel, whatever. I'll just put platinum, okay? The next one, we're taking the terminal alkyne and we're converting it to the geminal dihalide. Now, this is a Markovnikov addition. This is Markovnikov of HBr, right? And it's happening 2 times. So what do we need to do that? Well, I'll use a different color here. Okay, so to do the Markovnikov addition of the HBr 2 times, we're just going to use excess HBr. So we need excess HBr. And I'm going to go up to this one here because you see that this one is a Markovnikov addition of HCl. So I'll write here Markovnikov addition HCl. But you see that it only added once. And so instead of writing excess like we did in this one, we would specifically say, or I'd say 1 equivalent of HCl. So what it means, 1 equivalent, is if you have 1 mole of this, you react it with 1 mole of HCl, right? If you have half a mole of the alkyne, you react it with half a mole of HCl. All right. What about this reaction down here? So this one, could anybody answer, would this be a Markovnikov addition of water? Markovnikov addition of water across that triple bond, or anti-Markovnikov addition of water across that triple bond? We have an aldehyde here formed from our terminal alkyne. Yep, absolutely. Thanks, Isaac. It's anti-Markovnikov. So I'll just put here anti-Mark addition of H2O. And for that, it's similar. It's not identical, but it's similar to the anti-Markovnikov addition of water across a double bond, right? For an alkene, let's say you had an alkene, an alkene like this, okay, and you wanted to do an anti-Markovnikov addition of water, the first step was going to be borane and THF, and the second step was going to be H2O2, so H2O2 and sodium hydroxide, right? And in that case, here you'd end up with not very pretty drawing, okay, but you would end up with this compound here. So that's the anti-Markovnikov product. But anyhow, I digress. So if we go back here, you remember that we needed a hindered borane instead of borane, just regular BH3 and THF. And so there's several hindered boranes. We said dicyamylborane. We said sometimes we just write R2 BH like that. That's totally fine. Sometimes students will put 9-BBN, which is 9-borobicyclononane. Anyhow, either one is fine. They're all perfectly acceptable. And so we do that. And I also told you that sometimes in the ACS or the DAD or MCAT, they do this thing where instead of writing R2BH, they'll do this, where they put the boron in the hydrogen like this, and then they'll say, well, it's part of some big bicyclic ring. So this is kind of their shorthand for a bicyclic ring like 9-BBN. Okay, so Isaac told us that that last one was an anti-Markovnikov addition of water, and this one here is going to be a Markovnikov addition of water across our triple bond. And so for that, you know, this, what are the Markovnikov conditions for adding water across a double bond, right? Let's say you wanted to do this, okay? You would just treat it with H3O plus, right? And that's going to give you Markovnikov addition like that across an alkene. But in this case, you can't just use sulfuric acid and water and say, there you go, done, because when I mix sulfuric acid and water, I have hydronium ions. No, the reason that doesn't work is because you can't form a vinylic cation. It's too unstable. And so you need mercury to promote the reaction. So it's mercury 2 and HgSO4. You can call it either mercury 2 sulfate or mercuric sulfate. Either one is perfectly fine. All right, could anybody tell me for this next one here, we're changing the carbon skeleton. Here we have a total of 5 carbons, and here we have a total of 4 carbons. Could anybody tell me what the first step in this reaction would be? Notice that, again, we're changing the carbon skeleton. We're removing a carbon. Does anybody know what the first step would be in this one? We're taking a terminal alkyne. We're losing a carbon, but we're ending up with a carboxylic acid. Yeah, absolutely. Thanks, Rubio. Yeah, it's ozone. This is ozonolysis. So the first step is ozone, and then the second step is water when we have an alkyne. Now, something that they left out here in the slide is not only would you get this carboxylic acid, but you would also get carbon dioxide. Because when you have a terminal alkyne, this carbon here, if I just highlight that carbon in green, okay, that's this one here that ends up in the carbon dioxide molecule. Anyhow, and the last one is one that I want to make a note of, this one here, because it might be a knee-jerk reaction to say, well, I'm taking the alkyne that's terminal and I'm converting it to an alkene that's terminal. I can use whatever conditions I want. Well, actually, you can't in this case. And I mentioned it in class, but I'm going to write it down here. Let me get my purple pen. So this is special, okay? So the way you'd have to do this is using hydrogen in Lindlaier's catalyst. Or you could say poison catalyst is totally fine. If you're trying to reduce a terminal alkyne to a terminal alkene, you cannot use sodium metal reduction. So you can't use sodium metal in liquid ammonia. It doesn't work. You have to use hydrogenation for that. Cannot use, okay, sodium metal reduction for that reaction. Okay, it's just kind of an aside that is mentioned in the textbook, but there you go. Now you know. Okay, let's try some drawing some products of reactions. So here we have, it just says predict the final product for each one of the reactions, for each sequence of reactions. And we could try and draw some intermediates along the way. We don't really have to, but we could try. But you guys know that if I have a geminal dibromide and I treat it with excess sodium amide, it's going to do a double elimination followed by a deprotonation, and that's going to give me this. So if I count my carbons carefully, I have 6 carbons in the ring, and then I have 2 carbons outside of the ring. So I'm going to have a terminal alkanide like this. That's after the first step. And then in the second step, I'm going to treat it with ethyl chloride. So if I have ethyl chloride, which looks like this, I'm going to do an SN2 on my primary alkyl halide, which is going to give me this compound. So you'd call this cyclohexyl ethyl acetylene, I guess. But anyhow, and then the next step says hydrogenation with Lindlar's catalyst. Well, remember that enables you to form the cis alkene. And so after the last step, what we end up with is something that looks like this. So we're going to have our ethyl group over here, and then we're going to have our cyclohexyl group like this. And there you go. So there's the final product, just like that. Give me a thumbs up if you're with me on that one, okay? Mainly the first step. Cha? Okay. So remember, it does one deprotonation. So there's 3 protons on this methyl group, right? I'll pencil them in. And I know you probably follow along with me, but I just want to be sure because it's important. So the first proton gets removed to make the first double bond. Then the second proton gets removed to make the second double bond. And then the third proton gets removed to make the carbanion, to make the negative charge. Okay, so that's how that whole thing works. So if we try the next one, this is a great question. I think it's a really important question. It's just the first step is dealing with an alkylation, right? You're taking acetylene, right, and you're treating it with sodium amide. So after the first step, you're going to have sodium acetylide. So again, I'll write the name here. This is called sodium acetylide. It's actually used as a reagent sometimes. Okay, you probably, if you've been doing the practice problem, you've probably used it as a reagent a few times already this semester. So we have our sodium acetylide. Let me draw a little prettier lone pair. There we go. And then in the next step, we're going to hit it with iodomethane, which you guys know is one of the greatest electrophiles in the history of people, I guess. Anyhow, so what's going to happen is we're going to get nucleophilic attack, loss of leaving group, and then we're going to end up with propyne. Okay, so we end up with propyne. You don't have to call it 1-propyne, that's redundant. So we end up with propyne. And then the last steps is we're doing an anti-Markovnikov addition of water. Now, I didn't talk about the enol in the last problem, but we could try it here. So we have 1, 2, 3 carbons. The hydroxyl is going to end up on the least substituted carbon, and then the double bond will be here. Well, keep in mind, this enol is not very stable. It is going to undergo tautomerization. So I'll put here T-A-U-T. And then it's going to give me an aldehyde. So the aldehyde you would have is this aldehyde, which is propanal or propionaldehyde. Both names are perfectly reasonable for it. Okay. So there you go. So remember, the last 2 steps here are the anti-Markovnikov addition of water. So it's not the rich getting richer, it's vice versa. But we end up with an enol that tautomerizes to give us an aldehyde. In the next one, the first steps are basically the same as the last one. You're just changing the methyl iodide to ethyl iodide. So after the first 2 steps, we're going to end up with this compound. So CH2CH3, like this. Actually, that's not the prettiest, is it? Let's try and beautify it a little bit here. So we have 1, 2, 3. There we go, 3 bonds. Then we have methylene and a methyl. Still not pretty. There we go, and there we go. All right. So now in the last 2 steps, what we're doing is a Markovnikov addition of water, and so what we're going to end up with is something that looks like this. So we're going to end up with an enol that looks like that. But remember, that enol is not stable. Okay, it's going to tautomerize. So we'll put here tautomerize, and it's going to give us a methyl ketone. So we end up with this compound here. And you'll learn how to name ketones in organic chemistry too, but this would be called butanone. Butanone. So you can see the ketones end in -one. All right, there we go. So these are really great questions where it just gives you a starting material, gives you the reagents, and just kind of tests you. Do you know what the reagents make? And then something you have to be on the lookout for in this chapter is, okay, if I make an enol, what is it tautomerize to? Is it going to tautomerize to give me a methyl ketone, or is it going to tautomerize to give me an aldehyde? Okay, let's get into the most challenging, but some of the most important questions in the whole chapter, which are synthesis problems. Okay, you're going to see a lot of these in organic chemistry too. I'd say more than half of organic chemistry too is just about synthesis. So it'll say you're starting with a reactant and how would you make the product, okay? And sometimes it's effective to do a retrosynthesis. Other times we don't have to. We can try one for this one, but you can see that if you started it with 3-hexyne, okay, if you started it with 3-hexyne, and then you just did a hydration reaction, so just, you know, Markovnikov or anti-Markovnikov addition of water, you're going to end up with an enol. Either way, there's no Markovnikov or anti-Markovnikov to speak of here, and so you could use hydroboration oxidation, or you could use sulfuric acid and water with mercuric sulfate. Well, the second one that I mentioned is only one step, whereas hydroboration oxidation is 2 steps. So I would choose sulfuric acid and water with mercury 2 sulfate, but either one would be completely fine. Now, we've got to find a way to get from here to here, but you can see that we're adding 2 carbons. Right here, we've got 4 carbons, and here we've got 6 carbons. And so what do we have to do? We are going to deprotonate. So step 1 is going to be sodium amide. Step 2 is going to be ethyl chloride, bromide, or iodide. Let's pick ethyl iodide. We'll be high rollers. Turns out the iodides are the best, right? Because iodide is the best leaving group out of the halogens, but it's the most expensive as well. Anyhow, and so in the last step, all we're going to do is a hydration. So we'll put sulfuric acid, water, and mercury 2 sulfate. And there you go. All right. And again, you would end up with an enol. I didn't write it down here, but you would end up with this enol. Okay. And that enol is going to tautomerize to give you that ketone. And again, for this step here, I'll put here, you could use 9-BBN in the first step, or R2BH, whatever, and then hydrogen peroxide and base in the second step. Either one is fine. Okay, I mean, I would accept both. Okay. All right, next one, we have another change in the carbon skeleton. Sorry, I kind of took up a bunch of the real estate here. We'll just kind of, there we go. All right, so we're starting it with 4 carbons, and we end up with 4 carbons. So 4 carbons and 4 carbons. And we saw a problem similar to this last week, where if you have the geminal dihalide, I mean, it kind of is screaming at you. You need, do a double elimination. So if we do excess sodium amide followed by H2O, that's going to give us 1-butyne. And then if we want to reduce that to the alkene, well, I told you, you can't use sodium metal reduction to reduce a terminal alkyne. You have to use hydrogen and palladium platinum or nickel like that. Okay, next one, also in a similar vein. Right here, we're adding, look, here we have 4 carbons, and here we have 1, 2, 3, 4, 5 carbons. So we're adding 1. And the only way we know how to add a carbon to a molecule so far, and we'll learn more ways in organic chemistry too, would be to have the butyne conjugate base, okay, this compound here that I've written in blue, and then to treat that with methyl iodide, and then after that, we could do a reduction with Lindlar's catalyst. And so to get from here to get to this compound, so I guess along the way, I'm going to have to make something that looks like this. Okay, well, anyhow, so what do I have to do? I have to do the double elimination reaction. So I'm just going to get this out of the way. So first thing I've got to do is a double elimination. So I'm going to treat this with, excess sodium amide. Okay, and then instead of putting water in, or H3O plus, instead of adding water in and then deprotonating again and then adding the iodomethane, after you treat it with excess sodium amide, you're actually going to have, okay, you're going to have this. You're going to have the carbanion like that. And so now you can just treat it with methyl iodide, and that's going to give you the 2-pentyne that you want. And then to reduce it to the transalkene, we're going to use sodium metal reduction. And there you have it, my friends. All right. Let's see. How many more? 1, 2, 3. Oh boy, I put a lot in here. Okay, let's just do a few more. Everybody follow me so far? Everybody good so far? Any questions about these ones? The alkylation is super important, okay? Like I told you, it's not guaranteed, but one of the best ways to win a Nobel Prize in chemistry would be to find a way to make carbon-carbon bonds. And, we learn how to make bonds like this one here, right? Between the methyl group and so between these two carbons. And so if this is the only way we really know how to make a carbon-carbon bond so far in this class, you can imagine it's super duper important. So it's going to come up all the time in organic chemistry too. Obviously, it's coming up a lot in this class, and so it's super important that you're able to do that. Now that I said that, the next two questions have no change in the carbon skeleton, but you can see that if I want to make a methyl ketone, so here I have a methyl ketone, and just thinking in terms of retrosynthesis, what would I need? In that case, I would need to have 1-butyne, and then I would have to do a Markovnikov addition of water. So Markovnikov addition of H2O, and that's going to give me an enol, which will tautomerize to give me the methyl ketone. And so to make that terminal alkyne, all I have to do is take this geminal dichloride and treat it with excess sodium amide. Not amide, that's not a thing. Followed by water, that's going to give me the 1-butyne, and then all I have to do is a Markovnikov addition here. So I'm going to do sulfuric acid and water and mercury 2 sulfate like this. And of course, that's going to give me this enol. I'm sure you don't need my help with that, but anyhow, that enol is going to be unstable. It's going to tautomerize to give me the ketone. The next one, kind of a weird question. I don't know why you would want to make this dibromo compound at the end, but I suppose you could do it. If you had 1-butyne, you would just treat this with one equivalent of Br2, and it would give you this compound here. And, mostly it would give, it would give you mostly the trans. And so you have to make 1-butyne. And so I don't like to say straightforward in an organic chemistry class. I don't think it belongs in the class really. But you would treat this with excess sodium amide followed by treatment with water. That's going to give you this compound. And then you would just treat this with one equivalent of bromine. Okay, if you used excess bromine, so let's say you used excess Br2, in that case, you would end up with this compound where you'd have 1, 2, 3, 4 bromines like that. Okay, so that's something completely different. So maybe I'll put that in a different color. Oops, that's not what I meant to do. All right, but that was one of the questions that we did talk about in the class. So here we go. All right, next one. We have an alcohol here, and so we could make that alcohol by a Markovnikov addition of water to 1-butene. Right, so we just have to do Markovnikov addition here. And so we already know how to make the terminal alkyne. We treat it with excess sodium amide followed by H2O, and that's going to give us 1-butyne. Then to make 1-butene, to make this compound, we're going to hydrogenate with Lindlar's catalyst, and then this part here is just going to be a hydration. No carbocation rearrangements to worry about, none of that kind of stuff. So there we have it. All right. Let's try a couple more. Let's see here. The next one, we're taking this alkene and we want to convert it to an alkyne. And so really the only feather we have in our cap for this would be to have, so if I hate drawing 4-membered rings, but anyhow, if we had, let's see, if we had, yeah, if we treated it with bromine and then we made the dibromo compound, then we could do a double elimination. So if we had this compound where you had a bromine on each end, right, you could do one elimination with this proton, you could do another elimination with this proton, and that would give you the triple bond. And then you could remove this proton, and that's going to give you the alkanide. And so then you would just treat it with water. So that's the answer to the problem. So all we're going to do is treat it with, we could say here, bromine, and that's going to be an anti-addition, but it's not going to be pertinent. So we're going to end up with one here and one here. And so then all we have to do is treat it with excess sodium amide, and then we just quench it with water and we're done. And there you have it, folks. Okay, let's do one more, and I'll leave you with C. C is pretty straightforward. You have 1, 2 carbons here, then you have 1, 2, 3, 4, 5. So all you're doing is adding propyl iodide to the compound. But this one here, we're starting out with 1, 2, 3, 4, and we're ending up with 1, 2, 3, 4, 5, 6. So we need to add 2 carbons. And so the first thing we're going to do is add those 2 carbons because it's the only way we know how to do it. So we're going to use sodium amide followed by ethyl iodide. And so that's going to give us our 3-hexyne, this compound. Okay, and then to get from here to here, we're just going to reduce, right? This is a transalkene. And so we're going to reduce with sodium metal and liquid ammonia. And there you have it. Well, I guess we'll do the last one. So we need to add 3 carbons, meaning these 3 carbons here. So the first step is going to be deprotonation with sodium amide. Second step is going to be, you could choose propyl bromide, propyl chloride, propyl iodide. I don't care. I'll just choose propyl bromide just arbitrarily. And so now we're going to have 1, 2, 3, and then we're going to have our cyclohexane over here like this. And then to reduce all the way down, we're just going to use hydrogen, and we'll use palladium this time. There you go. So that's a little bit of practice. Again, I think it's a really good idea to go over this question a few times. This one here, 9.37, where it just kind of quizzes you on most of the reactions that we learned in the chapter. All right, I hope you find this helpful as you're studying for chapter 9. And just keep in mind, if you find the learning all the reactions a little bit cumbersome, the good news is that we're pretty much done with the new reactions. When I say pretty much, I mean not completely. So in chapter 10, you do learn about 1 or 2 new reactions, but chapter 10 is mostly conceptual. And so once you get to chapter 11, which deals with synthesis, we've covered 95, if not more, percent of what's covered in chapter 11, which is basically considered a review of organic chemistry 1 to a certain extent, not completely, but there we go. So I'm going to turn off the recording. All right.